morning. Okay, all right. Thanks everyone. Welcome to class. It looks like the course website. Okay, so as with every Monday, we're gonna do a quiz today. You can go to quiz 3 on the course website. This link should take you to the quiz, which is now open. As a reminder, I guess it's still. Let's see. Yeah. So if you can get to the course website, the current link will take you to quiz 3. I use this to take attendance. So I do expect everyone to submit at least one attempt during the 10 minutes that I give you. If you cannot get to the course website because it was blocked, which I will try to fix, I just posted the link on Piazza. You can also try manually typing it in. It is here. I believe this takes us to the right. That's the wrong link. It's the wrong link on Piazza. Okay, Piazza now has the right link. Let me double check. Yes. Okay, so Piazza should have the quiz link as well. So if you can't get to the course website, head over to Piazza. The link is there. You can also try typing it, which I guess is a little complicated. But yeah, I'll give everyone a couple of minutes to at least submit your first version of the quiz. Again, the quiz is going to be open until midnight, but when you submit, your time of submission gets recorded. So that's how I track attendance for the week. Okay, so you want to make sure you do it while you're here. Any questions? Anyone still having issues with getting to the quiz? Okay. Is this Wi-Fi issue like just today, or is it like? Okay. In general, when that happens, Mondays and like Wednesdays are the first days for Wi-Fi. Got it. That's awkward. Well, again, I'll leave the quiz open until midnight. So if you can get it done when you get home, that would be great. Or when you get access to Wi-Fi. I'll leave this link up here. You can also try to do it on your phone. I think it's going to be a little tougher to do it on your phone, but yeah. What about folks on Zoom? Are you guys able to access the quiz?
Yeah, I am.
I can get to it.
Yeah.
Yeah.
Okay. Yeah, you guys got it. Okay, thank you. Yeah, so again, I do use the quiz to track attendance. But yeah, if I will take into account that there's some Wi-Fi issues. So. If you are on the quiz, this is what it should look like. So again, it covers the material from last week. Actually, maybe, yeah. So how many people are having issues getting to the quiz? Can you raise your hand? 1, 2, 3. Okay. Okay, so it's the minority of the class. Yeah, just try to get it submitted by midnight as always. Okay, so it's not that big of a percentage. Do you have a laptop? You don't have, you forgot to bring it. Do you have your phone? I have an iPad. I just want to do it at home. Uh, oh. Hmm. Ugh. This is on my account, but it does still ask you for your email. So you can try it on here if you want. Yeah, in general, like you don't have to bring a computer, I guess, most days, but on Mondays when we do the quizzes, then cool. I see there can be a question here. Oh, okay. Yeah, no worries. For the people that were able to find the quiz, how's it going? Are you feeling comfortable with all the answers? Except for the recursion. That one, I think it just might take a little bit more time to do because they're all very similar to each other. So you kind of have to think it through. But I do think I'm pretty confident you guys can do it, actually. Okay. I'm going to call it for the week 3 quiz. Again, this is open until midnight. Please try to submit at least one version before the end of lecture so that I can mark that you came to lecture today. Okay. That goes the same for the folks on Zoom. So please try to get one submitted before the end of lecture so that I can mark your attendance. All right. So let's get lecture itself started. So we're in lecture 11. Just a reminder, homework 3 is due Wednesday at 11:59. All right, so everybody's well aware of that. I've seen a few submissions already coming in, but please don't leave it to the last minute. There is also a homework 3 walkthrough video that is linked from the course website. So if you're struggling with the homework, you can take a look at that. But I encourage you to try it on your own at first, and only when you get stuck do you want to like sort of take a look at the video. Quiz 3 is going to be due at midnight. It looks like the course website is blocked on the student Wi-Fi. I'll email them again and see if they can get that fixed. Okay. Cool. Yeah, and NCAT's being funny. All right, so today we are going to be covering Radix sort, and we're going to be wrapping up the sorting algorithms and the divide and conquer technique that we learned. All right. So from last time, right at the end of the lecture, we introduced this idea of counting sort. So again, counting sort essentially follows the process where you create a bunch of buckets for your elements, and then you iterate over the array and put the elements into the bucket that they belong, right? So what is different? Like this sorting algorithm takes linear time. Why is this not in conflict with the statement from last lecture where I said that all comparison-based algorithms are at best n log n? Yeah, Vincent? Yeah, so we're using extra information. Okay, that's what makes the difference. For the comparison-based algorithms, the only thing you know is whether one element is bigger than the other. They don't have to be numbers. They don't have to be, they can be anything. As long as you can answer the question, is A bigger than B? Then you can use a comparison-based sort. With that restriction, there is nothing faster than n log n. However, for counting sort, what we're taking advantage of is one, we're taking advantage of the fact that these elements can immediately be put into buckets. So what that means is that they're hashable. So most of the time you see counting sort used with numbers or strings, okay? The other thing is we are taking advantage of the fact that we know that 9 is the biggest element in our array. So we pre-create all of the buckets from 0 to 9, all right? That's what we just covered. That is what we're assuming. We need to be able to know what bucket to put something in. So we assume that we can look at a single value and immediately put it into its bucket, okay? And we need to know that what values might show up ahead of time from the array. So for example, would you use bucket sort in this array to sort this array? Okay, I see some folks shaking their head no, why not? Yep, that's exactly it. The range between the numbers is very large. 2 to the 1000 is going to, you will have to create buckets from 0 to 2 to the 1000, which is basically going to take up multiple gigabytes of memory. And that's just to sort an array that has like 5 elements or 7 elements, right? So if you just use insertion sort, that would be faster than even just creating the buckets. Okay, so there are cases where we don't want to use counting sort. Yeah. As you guys mentioned, there would be a lot of buckets in this example. So there is an improvement on counting sort called Radix sort. So what is the what's the fundamental problem with counting sort that we just noticed? If the range of the numbers is very large, then we need to create a lot of buckets. Okay, so the idea with Radix sort is that you can actually split your input numbers into pieces and create buckets for each piece. So then you know that each piece of your number is not, the range is not too large. So a very, very clear example for this, which you're going to walk through. Radix sort in general can use less space than counting sort, and it's for sorting integers up to a size m. Okay. In counting sort, we use counting sort on the least significant digit first to sort all the elements by the least significant digit. And then we sort them by the next least significant digit using counting sort as a subroutine. Again, so for example, we're going to walk through an example. So if you're not understanding that, that's fine. If you're trying to sort the numbers that go up to 1000, you would not necessarily create 1000 buckets. Instead, you look at each digit and you create only 10 buckets. Okay, and you sort digit by digit. So here's an example for first, we run counting sort on the least significant digit. So what does that mean? That means that first we sort by the ones place. Okay. So I created only 10 buckets because I'm only sorting by the nines place, right? So that means that 21 goes here, not because it's 21, but because it has a 1 in the ones place, right? 345 goes there, 13 goes there, 101 goes there, 50 goes there, 243 goes there, and 1 goes there. Okay. So again, this is how the algorithm works. This is our first pass trying to sort things. we sort by the ones digit. Is that clear to everyone? Okay, so now what we're gonna do is we're gonna go, so now our array looks like this. So we started with this array, and now it looks like this. What do you know about this array? You know that if you ignore all the numbers except the least significant digit, this array is sorted, right? Because you have 0, 1, 1, 1, 3, 4, 5. So by the least significant digit, this is sorted. Obviously, 101 one should not be here. It should be somewhere else. So it's not entirely sorted, but we have now sorted by the least significant digit. Okay. So what do we do next? What do you guys think is the next step? Yeah. Yeah, you sort by the second digit. Okay. So you take this array and you've sorted by the first digit already. So now what you're going to try to do is you're going to sort by the second digit. So let's see what that looks like. So again, we take this array and now we sort by the second digit. So that means 50 is going to go there. 21 goes there. 101 goes here. 1 goes here. 13 goes here. Actually, yeah, why does 1 go here? Because the second digit is 0, right? 13, 234, and then 245. Okay, so again, we're using another, so we do counting sort again, but now on the second least significant digit, and then we put it all together. This is what our array looks like now. So what do you guys notice about this array? It's not fully sorted yet, but it is now sorted by the first two digits. 0, 1, 0, 1, 13, 21, 34, 45, 50. Okay, so it is not fully sorted because 101 definitely shouldn't be here, right? But now we have sorted by the last two digits of all of our elements. All right. And again, so one key property why this works is because the sorting is stable. I won't focus too much on that, but what do you think is the next step? So the next step is we sort by the third digit. So 101 goes here, 1 goes here, 13 goes here, 21, 234, 345, 50. And this is what we get when we put them together back in order. We get 1, 13, 21, 50, 101, 234, 345. And now what do you guys notice about this array? It is sorted by the first 3 digits. And in our case, none of the numbers are greater than 3 digits. So now it is fully sorted. Okay. So this is an alternative sorting algorithm that is not comparison based. That is using the fact that 1, we have numbers. 2, that we can break them up into pieces. And 3, that when you sort piece by piece cumulatively, that is equal to sorting by the whole thing. So that's actually called lexicographical sorting. There are other sorting things you could imagine doing, but for this one, that's how it works. So again, why does it work? So this is the array we started with, then we went to here, then we went to here, then we went to here. So as you guys already pointed out, the reason it works is that in the second array, everything is sorted by the first digit. Everything gets sorted by the last 2 digits. And then at the end, everything is sorted by the last 3 digits, which is just all the numbers are at most 3 digits. How do we prove it? So given this iterative process where at each step we sort by an additional digit, if you guys wanted to prove this formally, or not even formally, if you wanted to be convinced that this works, what would my inductive hypothesis be? Or my base case? Yep. For the base case, is that what you're going for? Maybe. Okay. There's something to do with digits. Okay. So you guys remember, how did I convince you that it was working? I told you, okay, so on the first step, we sort by the first digit. And then I said on the second step, now the first 2 digits are sorted. Yeah. Yeah, so the base case is an array is sorted by 0 digits by default, because you're not looking at anything, I guess. So like any array is sorted by no digits at the beginning, right? And then that gives you a hint to what the inductive hypothesis looks like. So the inductive hypothesis would be assume that I have an array that is sorted by the last k digits. So by the last 3 digits, let's say, or the last 2. So here I have an array that is sorted by the last 2 digits. In one step of this algorithm, I have to show, or you have to be convinced that after I run one step of the algorithm, I will be given an array that is now sorted by k plus 1 digits, right? Now, if you show the base case for k is 0, which is trivial because every array is sorted by no digits, and you show that when you have previously an array that is sorted by the last k digits, right? If I can convince you, if you're convinced that I can go from sorted by the last k digits to the last k plus 1, you have now proven the algorithm works. Okay? Because you can start at 0 and you say, well, k is 0. He already told me that if for any k plus 1 works. So it must be sorted by 1. It must be sorted, right? Okay. So the inductive hypothesis is that after the kth iteration, the array is sorted by the first k least significant digits. Okay. The base case is sorted by 0 least significant digits, which holds for any array. Okay. So it's like you should be convinced that that's true. And the inductive step is the one we're trying to do. And then the conclusion would be, because this inductive hypothesis holds for all values of k, then after the last iteration, my array is sorted. Okay. This is the part that is like the interesting part. But again, you guys like intuitively, you are already convinced the algorithm works. But if you're trying to show somebody else, like, yes, this algorithm sorts my array, right? It's not obvious. If I didn't show you the pictures and I just told you what the algorithm does, would you guys be like, oh yeah, the final array is going to be sorted? Okay. Yes, so radix sort is correct. So we want to focus on this inductive step. So after the kth iteration, the array is sorted by the k least significant digits. We're going to assume that is true. Or that's what we're trying to prove. So we're going to assume that it is true for the previous iteration. And we're going to show that it proves that it holds for the next iteration. Okay. So I'm going to go a little fast over this because, again, I don't necessarily expect you guys to produce inductive proofs. But this is the reasoning when you're working with algorithms that you want to walk, like it doesn't have to be this formal, but if you ever have an iterative algorithm and you're trying to think, is this doing what I want it to do? This is a good mental framework to be like, well, does it work for one example, my base case? Can I think of an example where it does work? And then can I show if in one step, if it worked before, will it work after the next step? Okay. So this is the example for I equals 2. So we said, if this array is already sorted, can I show that it'll be sorted by 3 digits after I run one iteration? Okay. So this is like formally how you might actually write this down. So you want to be really precise. Okay. This is saying my x consists of many digits. Okay. So this is like, for this one, 0, 5, 0, this would be x1 would be 0, x2 would be 5, x3 would be 0. So it's just saying, suppose I take an arbitrary number, it must consist of some digits, okay? And then I take y, it must consist of some digits. Now suppose that x up to I, if I drop everything except the I, like everything before, if I only keep the last I digits, so this is from I to 1, if this is smaller than y, okay, then I want to show that after my algorithm runs, x will always be before y. Like it will be sorted, okay? So the first case is actually pretty easy. It's that this digit, the ith digit, is smaller than y's ith digit, okay? In that case, x is in an earlier bucket than y. What does that mean? When I'm running counting sort on the ith digit, if xi is smaller than yi, then x, the number x, is going to end up in a bucket before the number y, right? For example, here we have, yes, x and y. So we're doing it for I equals 2. So we're looking at the second digit here is 1. Second digit here is 2. Okay. They're not sorted right now, but after I sort them, x ends up in a bucket before y, which means when I take it out, x is going to be before y. Okay. That's the first case. Second case is that xi and yi are equal. Okay. Now, in this case, we know that xi minus 1 is less than yi minus 1. So if we ignore the ith digit, and because x is smaller than y up to the ith digit, if the ith digit is equal, that means that the other digits must be smaller, right? Like this number must be smaller than y, which means that x and y end up in the same bucket, okay? But x is put in the bucket first. Okay, so that's this example where the second digit 0 is the same, but because we know that 0, 1 is less than 0, 2, that's what we're assuming, that must mean that 1 is less than 2, which must mean that by our inductive hypothesis, 1 came before 2 in the previous array, okay? Which means even though they end up in the same bucket, 101 ends up before 002. Like it goes into the bucket first, right? It goes because we iterate this way, which means it will end up before 02, right? So again, we're not looking at the third digits here. We're doing it for the I equals 2 case, assuming that it worked for the I equals 1 case, right? So these are the cases, like you guys shouldn't just believe me with an example. You should have thought through these cases and been like, is it true that after one iteration, if I assume the last I digits are sorted, is it true that if when I do one step, it will have the I plus 1 digits sorted? Okay. Now, this is just a proof sketch, but that should give you, this is essentially our inductive step. That should convince you more thoroughly that this algorithm works. Okay. That whole thing would go here into our inductive step of the proving that radix sort is correct, right? Any questions on the proof? Are you guys more convinced that radix sort does work? Not just for the example I showed you. Maybe I picked the numbers in a way where they would end up sorted. But now you guys are like, yes, it sorts by the first digit. And because it sorts by the first digit, when I sort by the second, it'll be sorted by the last two digits after the second iteration. Okay, cool. So again, in practice, having such a formal proof, not that important. It is important for you guys to be able to think through it and convince yourself that this algorithm is right. So I'm giving it to you. I'm telling you it's right. But if you ever come up with your own algorithm, you will need to I don't know, think through it and convince yourself that it's right. Okay. So the next question question.
So I have a question about the proof. So how do you show the inductive step without having the specific numbers? Because what if their argument is you set it up in a way that works? How do you prove that it matters without that?
Yeah, so there was a question on Zoom, which is how do you show the inductive step without the specific numbers? So I do want to clarify that this part here, this is not assuming any particular numbers. It is just saying X can be written as some digits and Y can be written as some digits. Now, the example I show you is to, in theory, you shouldn't need this. If I just read this to you, in theory, you should be like, okay, that makes sense to me. Here's my X's and my Y's, and this one's smaller than that one. But this is more to highlight concretely what a specific instance of this proof, right? Hope that answers the question. That's a good question. Thank you. All right, so now we move on. How fast is it? What's the running time, guys? Suppose I am sorting n d-digit numbers, okay? So I have n numbers, each one which has d digits in base 10, let's say. How many steps does my algorithm take in terms of n and in terms of d? Yeah, you give it a shot. O of n times d. What do you guys think? Isaiah? Okay, d plus 1, check it to make sure it's sorted. You don't ever have to check to make sure it's sorted, but there might be a plus 1 there, but turns out in the big O, it's not going to matter. Any other ideas for how fast the algorithm is in terms of n and d? So we already described, I didn't code it, so you don't have to look at code, but we described the process that we ideally would want to run. So there's n digits in my array, and then I run counting sort on them d times, right? Because for each digit, I like counting sort by the first, then I counting sort by the second, then I counting sort by the third. Okay, cool. So again, how many iterations are there? There are d iterations. How long does each iteration take? O of n time, because I'm running counting sort. So the total time is n times d. Great job. Cool. Is that good?
Professor?
Yeah, question?
Yeah, will it work for negative numbers, or how will that work?
Would it work? Okay, so there was a question on the class. Would it work for negative numbers? How would that work? Any ideas? Yeah, so one idea is you can try to create more buckets for both the positive and negative digits. So you can try to keep them separated. What's another idea? So this algorithm directly, as we described it, won't work unless you do what you said. So we create buckets that are for like negative digits and also positive digits. You can also remove all the negatives from your negative digits, sort that, and then sort your positive. And then you're like reverse the negative one, right? So again, like a lot of the algorithms. So another thing we did also, I think we're also assuming that all the digits are unique. So there are many things we assume when algorithms get first presented. So to answer the question on Zoom, this specific algorithm will not work with negative digits unless you do something extra to handle the negative digits. But doing something extra, we already have a couple of different ideas, will be at most O of n time. So one example is just take all the negative numbers, make them positive, sort that separately, because you know the negatives are always going to come before the positives in the end, right? So sort that separately, sort the positives separately, and then reverse the negatives and then put them together. Okay, and all of that takes O of n, so doesn't really affect the running time of the algorithm. So we would say it's just a modification. But that's a good question. So again, the algorithms you'll learn here, when you go do interviews, they might ask questions like these, right? So you've seen an algorithm for sorting positive integers, and they might modify it, so now you have negatives. So your job is to like figure that out. Cool. Now, is that good? So we said the running time was n times d. Is that good? What do you guys think? Yeah. So sort of. It depends on what your base is and how many digits you have, right? So to sort n integers, each of which is from 1 to n, let's say, so we know the maximum is going to be n, then the number of digits we're going to have is going to be log base 10 of n plus 1. Okay. So log tells you how many, the log function also tells you how many digits it takes to represent a particular number in a certain base. Hopefully you guys know that. So like, if I wanted to know how many bits it takes to represent 15, I would take log base 2 of 15. And that tells me how many bits, like zeros and ones it takes. If I want to know how many in base 10, how many digits it takes to do 15. If you do log base 10 of 15 plus 1, you get 2. So it takes 2 digits. Okay, because it basically counts how many times do I have to divide the number by 10 before I get to 1. So intuitively, you guys should know, like if I have 153, I have to divide it around 3 times to get to 1. And that's how many digits it has, right? For example, 1, 2, 3, the log base 10 of 1, 2, 3, 4 plus 1 is equal to 4. So it has 4 digits. So the time actually becomes n times d, but if my numbers are from 1 to n, then it's actually n log n. Right? So we just came up with this like crazy algorithm, very different from the others. And most of the time, it's probably going to be n log n. Same as merge sort. So that's pretty sad, I would say. But can we do better? So it is a different algorithm. So we're going to try to do better. And as somebody hinted at in the class, it kind of depends the base that you pick to represent your number in. Okay. So radix sort on base 10, which is the one we have been covering this whole time, because we're looking at only the digits in base 10. We're looking at 0 through 9, right? Is not a great idea. It'll be the same running time as merge sort. Okay. But let's say we change the base and set it to base R. So this is like an arbitrary base. Intuitively, a bigger R, so a bigger base, means that you have more buckets. So R, the base, is how many buckets you have, right? For base 10, we have 10 buckets. If we do base 2, we would have 0 and 1. Those are our 2 buckets. If we do base 1,000, we'll have 1,000 buckets, okay? At most, right? Because the whole point of radix sort is that you do it digit by digit, so it balances the number of buckets, all right? So bigger R means that I have more buckets. Bigger R also means that I have less digits, right? Does that make sense? So for example, if I want to represent the number 10 in binary, it takes 4 digits. Whereas if I want to represent it in base 10, it takes 2 digits, 1 and 0. Whereas if I want to represent it in base 11, it would take 1 digit, because 10, like we would say like 10 is like a digit, like in base 11, it's another symbol. It would be like 0 through 9, and then you'd be like A, and that's like 10. So it would take 1 digit. Okay. So the bigger the base, the fewer digits, but the more buckets. So for example, what if we tried base 100? Right, so instead of base 10 that we did last time, we do base 100. What does that mean? That means that we create 100 buckets. So now we have a lot more. But now, immediately, we sort by the first 2 digits. Because in base 100, this is like 1 digit. Like 0, 1, like 34, 50. In base 100, those are like 1 digit, because you can represent it that high. Okay, we get this array, which is now sorted by these 1 digit in base 100, but 2 digits in base 10. And then we do it again. And now the array is sorted, right? So it took less steps. It didn't take 4. It only took 2 steps, right? But we had to make a lot more buckets, okay? So intuitively, there's a trade-off between the number of buckets and then how many steps it takes you to sort the arrays, okay? Right. So for base 100, we only took 2 iterations of counting sort to sort the entire array. For base 10, it would take us 3 iterations of counting sort to sort the entire array. And we would have 10 buckets. So a bigger base means more buckets, but fewer iterations. In general, what's the running time? Say we want to sort n integers whose maximum size is m. Right, so this is the maximum value of any of the integers in base R. What is the running time of radix sort in this case? Yeah. N times log m. Okay, that is very close. Number of iterations, same as the number of digits, base R of an index x of max size m. So that's going to be log base R of m, just like you were saying. Okay, because it's how many digits will my biggest number have? This says it'll have log base R of m plus 1 digits. Okay. Now on each iteration, we initialize R buckets and put n items into them. Okay. So the total running time here is O of n plus R. So because now R is a variable, okay, right? So before we had R fixed, we were saying like, oh, we're going to create 10 buckets. We're going to create 100 buckets. So we didn't care about it in the running time because we were saying it doesn't matter. It's 10. We're always going to create 10 buckets. So like it's constant, right? In this case, we are now keeping R as a variable. So the number of buckets you create can actually change. So in the general case, the running time is O of D times N plus R, which is O of log this times N plus R, right? Now, you don't necessarily need to know this, but what you would do at this point is we're trying to figure out, like, essentially what we're trying to figure out is like, what's a good value of R to pick? What's a good base? What's a better base? Because we did at base 10, and that was still N log N. Base 100 is actually N log N as well. But the question is, what's a better base? What's the best base that we could use? These graphs, I just plotted them for different values. Like basically you're just playing around with M, with N and R to try to get a sense of it. There are many possible choices you can pick here depending on your problem. Like it's everything, it's a trade-off, okay? It turns out that a very reasonable choice for R is to set R equal to N. Why? So you don't even have to look at the charts. You would just be like, if you're trying to set a reasonable choice of N, why would you want N to be equal to R? Yeah. M is the number with the largest amount of digits. But one of the reasons we choose N equal to R is because then in this case, you can replace N plus R with N plus N, which is 2N, which then disappears in the big O. So you kind of get rid of R and you balance it out with N. That might be why you might want to pick N equal to R. This is one possible choice. There are other choices, okay? So if we do choose N equal to R, this is what your running time becomes. It becomes N log base N of M plus N, okay? When you distribute it out. So to sort N integers of size at most M, the time is N log base N of M plus 1, because now we said R equals to N. Okay, we said that was maybe a reasonable choice. So the running time here, it actually depends on how big M is, okay? Because if log base N of M is like a constant, then this is O of N running time, right? Because this is N times, and then in parentheses, you have some number plus 1. If log base N of M were a constant, then the running time would be O of N, right? So when is log base N of M a constant? When M is equal to what? Huh? So if M is less than or equal to N to the C, where C is some constant, then log base N of N to the C, the N's cancel and you just get C, right? So this is saying if my biggest value is at most some power of the size of my array, could be any power, it could be 100. So you can get really big values. But let's say you're trying to sort arrays of size 1,000. This is saying as long as my biggest number is not bigger than 1,000 to the 20th power, then radix sort will actually be linear running time in the size of the array. Now, if instead M was something like 2 to the N, so if the biggest value was exponential in N, then the running time would be N squared over log N. So if you plug in M equal 2 to the N here, you can rewrite this so the bases cancel and you get another N out in the front, so you get N squared over log N. So you don't necessarily need to know this, but I guess the main thing to remember is that if the number of buckets is equal to R, which we thought was a good choice, then if my maximum number is some polynomial of my size, so not too big, this means it's not too much bigger than how big my array is, then the running time of radix sort is linear. If, however, the biggest number I can have is exponentially bigger than the number of numbers I have in my array, then my running time is essentially N squared by a smaller factor. Okay, so again, for an example, what have we learned? We learned that radix sort can sort N integers of size at most N to the 100 in O of N time. right? If your integers have a much bigger size, like 2 to the n, then you probably shouldn't be using radix sort. The running time is going to be worse than merge sort. So you probably want to use merge sort. And it matters what base we pick. The other thing is this is just a constant, so I could put anything there. It's just saying as long as my numbers grow polynomially with my size, any polynomial, that could be 1,000,000, which means your numbers can be really big as long as they're like, this is why like big O matters, I guess, where it's like, they can be really, really big, but they can't grow exponentially with your size of the input. They have to grow polynomially, okay? So that's it for sorting. We have a couple of minutes, so I will cover a little bit of what we're going to cover. So we're actually going to do a little bit of review, I hope, for most of you guys from Comp 280. You guys covered trees. Did you cover hash functions? A little bit. Okay, so for this next week, we're going to be diving more in depth into self-balancing trees because it's important to know them. And we're going to dive more in depth into hash functions, which are very, very critical for some of the analysis of the algorithms we're going to learn later in the class. Okay, so we've got 3 more minutes left, so I'll just keep going. I'll try to wrap up. So again, a brief wrap up of what we have learned so far in the class. So this is going all the way back to lecture 1. Okay, so the thing that we have learned is this idea of divide and conquer. We used it a lot in many different algorithms. The idea is that you can take a big problem and you can split it into smaller problems and you can call yourself recursively. Okay. Now, how do we design a divide and conquer algorithm? We've seen a lot of examples of these algorithms. So we saw Karatsuba, we saw merge sort, we saw select, the select K problem. We saw quick sort, which is also a divide and conquer algorithm. Pick berries in homework 2 is a divide and conquer algorithm because you're making the problem smaller. Count sevens, also divide and conquer algorithm. Index match in homework 3, which you guys are doing now, can also be done with a divide and conquer algorithm. And majority vote in homework 3 can also be done with a divide and conquer algorithm. Okay. Now you don't have to do them with divide and conquer. There is a simpler solution, that like a slower solution, but it's simpler, but you can. So let's take a minute. We have exactly a minute actually to zoom out and look at the general strategy. So these are the examples of the algorithms you guys have already learned both through homework and through lecture that are divide and conquer. So divide and conquer is a very general strategy. Okay. So one strategy for solving any problem, if you want to use divide and conquer, is first, you want to look at your problem and see, are there any natural subproblems? Is there some way that I can split my problem into natural, smaller subproblems? For example, arrays of half the size, that's what we used in merge sort. Things that are smaller or larger than a pivot, okay? Once you have your natural subproblems, your next step is to imagine that those subproblems have already been solved for you. Okay, pretend that you already solved the problem you're trying to solve for the smaller problems, right? So what does it mean? Because what you want to do after that is if you pretend you've already solved the smaller problems, your goal with divide and conquer is just, what do I need to do in order to take the answers to these smaller problems to give me the answer to the larger problem? That's it. Once you have figured that out for an algorithm that works with divide and conquer, you essentially have the entire algorithm. Now you just need to code it. Okay. Now, how do you figure that out? How do you figure out what are my subproblems? You try different ways of splitting the array or whatever. How do you figure out how to put it back together? You work out through examples. You're saying like, hey, if this half of the array is sorted and this half is already sorted, you know, how do I put it together into the bigger sorting? Is that something that I can do in the appropriate running time, right? Is that something that I can do quickly? Yeah. So for example, you can think about how you could arrive at merge sort or quick sort using this strategy. Okay. Other tips, you should always try out small examples by hand. Another tip is part of this course is to teach you a lot of different algorithms. Eventually you will see problems and you will say, huh, that looks a little bit familiar to what I did before. It won't be the same, but you'll get that sense of like, wait, this merge sort kind of reminds me of binary search a little bit. Okay, quick sort kind of reminds me of merge sort a little bit. Case select kind of reminds me of quick sort. All right. And then the last thing, the last tip is you want to bring in your analysis, your big O analysis, because usually the goal is to design an algorithm that's fast. Okay. So if you remember when you do divide and conquer, if it takes you too much work to put the answers together, you don't even have to bother writing out the algorithm. You can just be like, well, how much work might this take me? Is this n squared, n cubed? And then by master theorem, you could say, oh, the running time is actually going to be n cubed for the whole thing. So I don't even bother. Like, that's not the right approach, right? Like, however I chose to split it, it's not the right one. Or there must be something else I'm missing because this approach is going to take too long. Cool. And then lastly, you just iterate. You just keep trying. The thing that is really frustrating that, we're over time. Last thing for you guys, it can be frustrating to design algorithms, but practice does help. And this says there is no formula for you to design algorithms, but very recently, February 2nd, DeepMind actually designed an AI to solve programming problems. So it's like you give it the description of lead code, for example, and it will write you a program that solves it. So we might be getting to the point where everything I'm teaching you is completely obsolete and we'll just have machines do the algorithm design, but we're not quite there yet. But yeah, thank you. All right, everybody on Zoom, thanks for coming, and I will see you guys on Wednesday. Thank you. Oh, yeah, of course. Yeah.